Welcome. The topic for today is offshore structures for oil and gas production. So, in any offshore field, we typically have an offshore structure that is the one that enables oil and gas production, where typically it gives services. It allows for services, it allows to send fluids, power to the wells, and also to receive the oil and gas and water produced and prepare it for to be sold on sold on the market. So in many fields, offshore fields, some offshore fields we don't have the offshore structure. We simply are either producing directly to the beach, to the shore, if the distance are short, or if I can do it. Or also I can produce to a neighboring field, to the facilities, existing facilities. But for most cases, I'm going to have some need to have an offshore structure to produce. So I want to go a bit briefly through the components that are typically included in this offshore structure. And some of them are the drilling facilities. So if I have to, for example, it could be that I am going to drill the wells from that facility. Um, uh, or I also am going to do frequent intervention or sidetracking or recompleting of wells, then I need to have all the drilling equipment. And this I can call the drilling package. So then I can have, for example, the tower you see here on let's change it to, okay, the tower, drilling tower. You can have also a storage place for the tubings, for the casings, uh, for the tubulars. And then I have the mud package, the cementing part, etc. And also I can have, not necessarily, but I might have facilities for light well intervention, for example, with wireline or coil tubing. Something the heart of typically an offshore structure is the processing facilities that you can see here to the right. So I have separation and stabilization of oil, gas, and water. Then the oil goes to further dehydration, desalting, and stabilizing, and then it can go shipped on a tanker or transported, pumped on a pipeline. The water is separated and treated, and it can be sent to dumped in the ocean, or it can be reinjected to another formation. And the gas is dehydrated and compressed and can either be sent through a rich gas pipeline to a gas processing plant, or it can be reinjected in the reservoir. Gas injection system, the gas compression units for pipeline and transport. The water injection system is also included in the offshore structure. Here is a schematic of a separator. They take a big amount of space, and you have a lot of equipment associated with separators, so usually that takes a lot of space on the platform. So other things we have are living quarters for the personnel that is working on the offshore structure. We have a heli deck to allow transportation to and from the structure. We might have sometimes some structures that are accessible via boat. We have power generation. We have typically this is done using gas turbines. We have the flare system. You see here the flare they take care of burning hydrocarbons, typically gas or oil that you might have if you have a maintenance operation, if you have startup, if you have also an emergency situation, you use sometimes a flare. Utilities, to have the hydraulic power fluid to operate the elements of the subsea system, the compressed air, drinking water, air condition, ventilation, and heating system. Another thing you might have in an offshore structure is a bay, what this is called a bay for wellheads and Christmas trees. In this bay, you have all the wells. We will see later what that means, but all the wells are the Christmas trees. They are dry, so a person can come and have access to them. Then you have the production manifold. There are sometimes on the offshore structure facilities for oil storage, oil offloading. If typically you have to ship, if it's oil, you have to send oil to a tanker, so you need to have a facility to transfer the oil to the tanker. Control system, monitoring system, a system for storage, injection, and recovery of production chemicals, for example, a wax inhibitor, scale, hydrate, or corrosion inhibitor, and repair workshop. Here you see an example. You have a a jacket, okay, where you have your offshore structure, your production facilities, but then you have a pipeline, and then you have here a facility in which the tanker connects, and they ship then the oil to the market. Typically, an offshore structure is built in a modular way because these modules are built on land, on a shipyard, or on the facilities of different manufacturers, and then it ships on a ship, on a vessel, and is transported to the structure. So you see here you have, for example, the living quarters close to the heli deck. You have the power generation module, the gas turbines. You have utilities. Then you have the drilling part with the drilling tower. And then you have here, far away from the living quarters, you have the processing module. You have the wells are here below the tower. And you have here, in this case, the water injection module. So everything is modular, and in many cases you see that they assemble it in a modular way. Also, one comment here, this is a Wellhead field. I think it's operated now by Aker BP, and they, in this case, they don't have everything on the same structure, but the things are spread. So I think the processing, it's in this case, it's this one. This has some processing, and I think here there is some processing. There are only wells here, and you can see the wells actually coming. You have some wells coming in here, wells coming in here, and the heli deck is, I think, actually here. And here you have a flare for the processing, and here you have another flare for the processing, and you have a drilling tower where the wells are. So this will be like a platform for wells. This will be a platform for the processing. You can have here one for the people and the processing. And here you have some other, you have, I think here might be also heli deck. So, and then you have bridges connecting this to be able to go from one to the other. So the types of offshore structure, we have essentially two types. They are described here to the left. You have bottom supported, and then you have floating. Bottom supported, like the name indicates, most of the weight of the structure is received or is held in place by the soil. Like in this case, you have a jacket that has the cross section is becoming smaller with as tall as it gets, and then you have some foundation piles that they are actually drilled or they are hammered into the soil to provide more stability. You have another type which is very common in the Norwegian continental shelf, which is a GBS or gravity-based structure, and in this case is made out of concrete piles, and it is simply laying down by its own weight, but it also has a suction anchor. So if I can sketch very quickly the suction anchor. Okay, something like on this shape that is hammered on the soil, and then you will have here some fluid inside. So this is the soil, this is the suction anchor, and then you have some fluid inside. That can be air, it can be water. Here. Okay. But then what you do is that you take here a pump and then you extract that fluid. And by doing that, you create actually a negative pressure here, and then that happens that causes that this suction anchor is digging deeper and deeper into the soil, and then it is going to simply be drilled or not hammered, but is going to penetrate more into the soil. We have a jack-up, which is similar to a jacket, but in this case you see the cross-section is not becoming smaller with depth, but the legs are vertical. And the idea here is this is mostly used for drilling, but the idea is that you can, so this in regular, let's again make another sketch. So the jackup in regular configuration has the legs up when it's being transported, when it's flowing, is moving from place to place. But then at some point, when it's over, exactly over the place where you're supposed to be located, or you're going to drill, for example, then these legs are lowered using gears, using a hydraulic system with gears. And after that, they reach the soil, then this is going to be elevated and over the sea level. And for example, in this case, you might have the sea level someplace here. So this is also standing, and they depend a bit, the way you use them depend a bit on the characteristics of the soil, but essentially the jacket is using these piles and its own weight, and the weight is laying on the soil. Then you have this one where it's its own weight and then has this suction anchor effect that by removing and creating a negative pressure in this cavity, then they enter into the soil. And then the jackup is also by its own weight, but in this case, the distance between the sea level and the deck is increased by, or is changing up and down, moved up and down. And then you have another type of structure that in this case is different than the jacket, but is similar approach, but these are for deeper water levels. And this is has the same cross section, because to make a cross section like that, you will need a base very, very big. So you have the same cross section, and you have some movement. Due to that, you have some movement on this direction. So what you typically use in this structure is that you put some tethers, just fix it with some goid, some cables to the soil, to the seabed. Okay, then you have, on the other category, you have floating, and then you have those that are neutrally buoyant, simply that they float by themselves. It's like they are have no, there is no effect of, so it's simply they are floating. And in this case, you have the ship FPSO. FPSO we have talked before, but stands for floating production, storage and offloading. You have a semi-sub, which looks, this is also used very much in drilling, this vessel, but sometimes can be used for production. You have this Sevan FPSO, that is the same FPSO but with a round shape. And then you have the Spar, um, we will see later. And then you have, on this category now, this actually is called, is also floating, but it's positively buoyant. So this means that this, as you see here, it has some cables, some tethers that fix it to the seabed. But if these were not in place, actually this structure will float, will go much at a much higher level than what it is now. Okay, so that's what is called positive buoyant. Okay, so on these ones at the bottom, we can say that they have significant movement. Okay, this one have some movement, but this one have significant movement, are usually moored. That means that they are fixed somehow to the seabed, either with different tethers. They use cables, they use chains, and the buoyancy is actively controlled with ballast. Okay, they have some tanks where they store seawater, and then they change the amount of seawater stored to change the height, or the difference between the elevation difference between the deck and the sea level. Let's go now very quickly through one by one. So you see here a jacket is in the shipyard and then it's transported to place, and it's very interesting to see some videos how they sink it, because after they're in place they have to sink it in a very careful manner. And there you see, in the jacket, you see you have these piles that are actually in each leg. They have the piles, the holes for the piles, and then they hammer it in place with a hammer that is simply driving the piles into the soil. And this is to make it stable, and because this structure is heavy, but it's not. It could have some movement if you don't anchor it in place due to the marine loads. Now the gravity base structure. It's you have seen this many times in Norway. It was very popular at some point, and it has these cement legs and it has the suction anchors. But also these tanks, some of them they are for liquid storage. So you can store, in this case, you have some storage place for oil, for example. The jackup, this is taken from the Volvo PDO. They are using a jackup, and you see here is these legs that come up and down. And in this case, they have a line from the processing facilities all the way to a tanker. Okay, and I think in this case they were using an FPSO that they later transferred to a tanker. The FPSO is essentially a boat that has everything on top, and this is the heli deck. You see here the flare. And there are a few things about FPSO that I think we should comment on. So first, the swivel in let's represent the FPSO with this shape. Is after all it is a boat, and then you have the seabed. Then you have wells. These wells we will see later, but actually I have a line that is carrying the production from these wells. Then I have a structure. Then I have a structure. Should move the. Let's make the boat a bit in another place. Okay, the FPSO is here, and then you have the riser coming up here. So one thing is that so the riser will have significant movement. This location in the riser, because it's going to be attached to some point in the FPSO, and then the FPSO is going to move up and down, and it's going to move left and right, like that. Okay, and also not only that, but the FPSO is not always going to be oriented in the same way. So if you have the FPSO, for example, if the waves go in this direction is fine, but if now the waves come on that direction, well, you actually want to change the orientation of the FPSO such that the waves don't meet it in a way that it will be dangerous and will cause, for example, issues that might it might sink. Okay? So the main idea with that is that, or the main idea of the swivel is a very smart idea. And the intention is, well, if this has to be fixed to the FPSO and the FPSO has to twist, okay, then this one will be twisted. So one option, okay, that is using a swivel is essentially I make here part of the FPSO that these two parts they are able to rotate. So I make here a structure called a swivel that it allows, so it moves up and down with the rest of the FPSO. It moves up and down, but it allows to be relative rotational motion between them. Okay, so this can be in place, and this typically is fixed in place with some mooring lines. Okay, this is fixed in place. So it's controlling in a way. It's moving. It can move up and down, but it cannot rotate. Okay, this the blue structure. But then all the rest of the ship they can rotate and they can adjust according to the direction of wind and the wave. Okay, so let's make that comment here. I think we have here a video. Here I'm going to put the link so you can watch it completely. What you see in this case, the swivel is located not in the center of the FPSO, but is located at the end, in one of the ends of the FPSO. To see all of these lines, are the risers that I told you before, that they are going up to the swivel, and they are fixed on the swivel. And the swivel is moored. Actually, it has some lines that fix it to the seabed. And that's what here is called the swivel. And then you see the fluid is coming up here. This allows, so the rest of the ship can rotate. This can rotate to accommodate to the wind and to the wave conditions, but this one will always remain in the same place. Okay, so let's see, this is the swivel. Okay, part of the swivel. And there are some more. This is how the swivel looks like in a more detail. Okay, so let's maybe play this one completely. So you can see you have different pipes, and this part is fixed, and you have the part that is fixed with the ship, the rest of the ship that is rotating. Okay, so here you might have different wells, or you might have different, also you have injection going down and production going up. And this part is fixed with the boat, and this part is fixed with the catenary lines. Here is another, a closer view of the swivel, how it looks like. Very smart. Okay, and it has some seals, of course, because I want all of the fluid that is coming in here. Okay, in this case is for injection. You see it's going down and then enters someplace into the pipe and then goes down. Okay, so one comment I have here is that the swivel can because it's the dimensions, you have to design them very specifically for the fluids that's going to be carrying. If you need more volumes, then it will be bigger, and then it will need to be more careful, the seals and everything is very costly. So many times there are a lot of constraints on how many fluids I can produce, okay, or how many fluids I can inject just due to the swivel, because it's a component that is critical, and to make it bigger is challenging. Okay, the spar. This structure again is floating and is moored here in place with this is moored here in place with these tethers. And here you see you have, for example, you have the two risers that they go to a from Subsea templates, they go to the spar, and then you have one export line that goes in this case to maybe to shore. Yeah, and it looks like that. You see here the tethers. So one thing that is interesting with the spar is that when you have a body which is round, okay, which is a circle, and you have fluid impacting that body, okay, which is the case of the spar. You see here that is round, and then you have currents, okay, and waves impacting it. So the fluid is going to follow a path around it, okay, and then at some point it's not going to just go down and then go ordered like that, but actually it's going to detach early, okay, and then it's going to create some recirculation, some eddies in this location. Also, maybe here I did it too close. Okay, it's not going to go all the way to the same center and then go down orderly, but then it will have some detachment. And this is called a vortex shedding. Okay, but also something very interesting can happen. Here you see, let's see, this is a demonstration from
an object vortices are formed in an aquarium that separates one end from the other, overflow, and we'll put the shadows wiggling around a bit.
You see here you have the flow going on this direction, and then you have a cylinder on the flow, and then you have this detachment process occurring. Okay, and that you can see a bit on the shadow, you can see the detachment. Okay, you can see this, you can see how eddies are formed. Okay, but something interesting that happens is that this detachment point, sometimes it will detach, so it will start to enter in some sort of a cyclic process. Okay, sometimes it will detach here, but sometimes it will detach here, and it will oscillate between these two detachment points. So the fluid might follow correctly until here, or it might detach early. And it will oscillate when it's low, is here is closer to the center, is closer to the middle, here is going to be up. And then when here is closer to the center, then here is going to be down. Okay, so you see this generates the following movement. You see it generates some forces that cause the cylinder to start to move and oscillate. So this is a big concern in spars. So for that, in that case, let's see this one. You see here the detachment point is fixed, but then you have start to have this oscillation, and these are also called von Karman streaks. Okay, that has the name of von Karman. And when you allow to have the movement, okay, this is vortex induced vibration, VIV. So then you see that actually you cause movement in the cylinder, which you don't want to have. Here is another example of two. Okay, the same thing is with piles, with other things, with chimneys that have that shape. So you see here, that's why if you see something curious about the spar, it's not here actually, but something curious about spars, typically they have these helical streaks. And the intention is that by doing that, they are actually avoiding this vortex shedding, or they are controlling the vortex shedding. So they break a bit the cyclic nature of the vortex shedding, and they make it less regular. Okay, so you see here you have on the left, I think it goes one by one. You have these streaks that are added to the cylinder, and then you have one where it has no streaks. This is the force on the cylinder, and you see these are forces between 8 and 30. But when you don't have the streaks, you see the forces, they are actually very, very high. They have a very periodic nature, okay, and they can cause more issues. So that's part of the issue, the reason why you can also see it in the chimneys that they have streaks. The Sevan FPSO, it's the same concept as the FPSO, is floating, but in this case you see everything around all the ship, it was taken out. Okay, it's not anymore a ship, but now it's simply the circle, it's simply the swivel. It's to avoid having a swivel on the ship. One advantage is that well, you have part of the same phenomena here. It's a cylinder, so you have the fluid approaching the cylinder, can cause some issues, but also that the space might be limited. So you might have to increase the diameter very much to have enough space for what you need. Okay, and also the storage. The FPSO has storage of oil, while this one has limited storage. The tension leg platform, what we mentioned before. So you have, in this case, you have 4 legs, and these are tethered. And you see these tethers, they are not hanging freely, but actually they are in tension. Okay, you have another approach here with 4 legs, and here you have even 3 legs. Okay, here you see a more detailed description. There is a field offshore Trondheim. It's called a Hydron that has this type of facility, this type of structure. And then you see here it's called tethers, and you have this on the seabed, you have something that ties where the tethers are tied to, and these are always in tension. So some smart thing about the TLP is that these tethers, as I mentioned, they are in tension. Okay, so whenever there is a disturbance, let's say there is a wave that moves it to that displays it, and let's say moves it to this position here now. Okay, but now this one will be in the same location. Then what will happen is that you cause on these tethers, you cause a force going on this direction, and then the force is actually going against the direction of the force of the excitation force. Also the same thing here. Okay, so this arrangement will cause that um, the TLP will tend to go back to its equilibrium position. Okay, the same thing if you push it, you have now waves or wind coming from this direction, then it will be pushed on the other direction. Then the force will appear on the opposite direction that as essentially will tend it to stabilize. So it has a self-stabilizing mechanism that no matter what excitation you have, force you have, then it will try to bring it to the equilibrium place. This is a compliant tower. You see the base, this is the seabed, slightly bigger, but then the cross section is constant, and then typically you have some uh, the cables that these just to restrict the vertical movement because this can be quite big. This is can be 400 meters. Semi-submersible, you have seen it for drilling. Mostly is used as a drilling ship or a drilling vessel, but they can also be used for production. They have very little storage, and yeah. So how do we select or how do we decide which offshore structure to use? These are some of the things that are taken into account. So first we have the water depth. Then we have something very important. It is the type of Christmas tree that we have. If, and that depends on the well intervention needs. If I have to replace the tubing often, if I am planning to do a completion modifications in the life of the well, if I have artificial lift or not. For example, ESPs, they have a life of maybe 2 years or maybe down to 6 months. So if I have an ESP, then I have to be able to go inside, retrieve the tubing and retrieve the ESP. Then if I'm not sure, so first I will have some initial wells and then I will drill some more wells when I get more information. These are infill drilling if I have that need, so then we will see how that affects. And the reservoir spread and structure. If the reservoir is very spread, so that means that I cannot drill everything from the same location, but I have to use several locations. Need for oil and condensate storage, for example, that in my remote location where the tanker schedule might be affected because it might be some times of the year where there is storm, there is iceberg, other things. So then I might need to have storage to avoid disruption or having to stop production. And also another factor that is used is the marine loads, especially the oceanographic environment. How, depending on the place where the structure is supposed to be, how wind, waves, and current affect the design. So let's go one by one. So the water depth, here you see a sketch. This I think is updated from 2 years ago. So you see a sketch where here on the x-axis you have the water depth up to 3,000 meters, and then you see all the different structures where they're used. You see jackets and gravity-based structures. These are up to 413 meters as the record. Then you have this compliant tower, which is like a jacket but linear and with a constant cross section. You see that they are used for the upper range of the jacket, 300 to 610. Then you see you have the semi-sub, which has this shape as a drilling ship. It can be used actually in every older range because it's floating, so it doesn't have much restriction on the. Then you have the TLP, and the TLP they do have a restriction on the depth because they have the tethers that they connected to the seabed. Okay, and then you see the spar. The spar typically used for for medium depth, okay, from in this case the 588, the shallowest, to 2003-83. And yeah, the FPSO is also used mostly also like the semi-sub because it's used in the whole range and it's used also for very deep development. I should say something here that I forgot to mention about the spar. That is that the spar has a considerable part. So a considerable part of the hull is submerged. So you see, you have some part coming out, but you have a considerable part submerged. So this makes it that is more stable. So that's why it's sometimes chosen, because it's actually stable. Okay, now type of Christmas tree. Here you have two examples. So if we have a reservoir, which is a so if you have a reservoir which is concentrated, so maybe you can drill all wells from the same location. Okay, so in this case we are using a jacket and then we're drilling the wells from there. But if you have a lot of pockets, you have a lot of the reservoir is very spread or split into a lot of formations. So then you have to probably use is better, because then you cannot reach all of them from the same structure. So then it's better to have subsea wells and on each reservoir. These are what we call the dry Christmas trees, and these are called wet Christmas trees. So in this case, some comments is that these are long deviated wells, which are more expensive. Wells are drilled from one location, so you don't need to mobilize the rig. In this case, simply you have the tower that is changing slightly the position, but they are essentially not moving much, only a few meters. But one disadvantage with this approach is that the startup must be delayed until all wells are drilled, because you don't want to be producing and drilling at the same time, because it can be that I have an accident. I could cause an accident when I'm moving all the drilling equipment. Okay, the BOP, the tubulars. Now, in this case of dry Christmas trees, I can make shorter and vertical wells, which is less expensive. However, in this case, I have to mobilize the vessel many times, because they probably are in different location. So that costs also a lot of money. Every time I mobilize the drilling vessel, I have to moor it, I have to fix it in place, so it's challenging. But however, in this case, the production can start in ramp-up mode. So I can start, for example, if I drill these wells first, I can just already, if the FPSO is in place, I can start production while I drill from these wells. Okay, so one thing is that if they are more spread, I can probably do deviated and extended reach wells, but then I need a bigger drilling package. And then this bigger drilling package causes more weight on the structure and causes more cost. So I want to take very quickly a discussion on something just to think about the weight. Okay, so in onshore wells, so I have first the conductor. Okay, that is real. I'm not going to put the hole, simply I'm going to say the conductor. Then I have the surface casing, and this casing is actually uh, transferring the weight on the conductor, and the conductor is transferring to the soil. Okay, so you have this weight transfer. So then you have the intermediate casing. Okay, then you have the production casing. You might have some other casing strings also. Okay, and finally you have the tubing, which is painted also, even though it's not like that, but it's painted in a different color. Okay, let's say that the tubing gets to that. So in onshore wells, you have this transfer of weight. Usually the weight is going to be transferred from the tubing to the production casing, from the production casing to the intermediate casing to the surface casing, and from the surface casing to the conductor, and finally from the conductor to the soil. So you have this transfer of weight, and yeah, and of course we need to have some uh, seals, because we don't want, that's another thing, that we need to have seals in between, because here is going to be, in this case you have an inner pressure, high inner pressure, and then you don't want it to affect that it will transfer, then here we'll have a leakage and have a leakage and leakage and leakage, because the conductor and the other casings, they don't, are not that thick, so they don't tolerate the full reservoir pressure. So that's why you have some that's why you have some seals that they prohibit for the outer casings, the outer tubular strings to be exposed to the inner pressure. Okay, in this case you have the annulus. In this case, this annulus should tolerate the reservoir pressure, but maybe not these ones. Okay, in this case, the other ones, they have to be protected, and I need to have a seal. So when we talk about, so in some, for example, let's say wells that are on a jacket, dry wells that are on a jacket, okay, they are typically drilled just like, so to say, dry wellheads are drilled just like onshore wells. Dry wells are just drilled just like onshore. So the only thing is that in this case, simply the conductor is stretched. Okay, so you have the conductor and it's stretched all the way. So here is penetrating some part of the in the soil, but you have also another part which is actually going up, and you have this that straighteners that just make sure that the transfer is, it occurs vertically. Okay, because you might have a situation where this might start to deviate, and then the transfer of forces or of the weight is not is not going to be on the same line, but you have some curvature. Okay, so you have these rigidizers that they make sure that they stay on the linear, okay, that they are on a line. But here the main point is that the weight is transferred to the soil through the conductor, but the structure doesn't take any weight. Any weight of the well. And by well, I say all the tubulars, but also the Christmas tree. Yeah. Well, if you start getting also, but there is also another arrangement when you start getting for so this will be for shallow water depth. Okay, but for um, deeper dry wells, well, you actually have a bit of a different arrangement. So you have also on the seabed, you have the conductor, you have the just do it here also, the intermediate, the surface casing, intermediate casing, and the the production casing. This is the production casing. And there, all of them are actually transferring the weight to the seabed directly. But what you have here is that you have, this will be your subsea wellhead. Okay. Then you put a production riser. And then here at the top, you have the tubing. Again, you have the tubing hanger. And this will be your tubing that will enter into. Okay, so in the subsea wellhead, you transfer weight of all of them. Most of the tubulars, they are transferred to the soil, but then what this is holding, so here, let's say, let's symbolize it like that. So this is held in place by the vessel. Okay, let's maybe make it like that. Okay, so this is holding in place the vessel. Um, uh, they hold the weight of the riser and the tubing, and also the Christmas tree. Okay, so this is approach when you want to have dry Christmas trees, because let's say you need to have frequent intervention, you need to have a pump, or you need to have access to the well. Okay, but the water depth is too high, so then it won't be possible. You cannot make this arrangement. Let's say you have a floater, you have a floating production facility. So in that case, what you do, you split the load. So a lot of the load, all the casings, all the even up to the production casing is carried by the soil with the conductor. And then you have a subsea wellhead, and then you have a production riser, and then um, you have the tubing that is so the tubing, the Christmas tree, and the production rider, all of their weight are carried by the vessel. Here, this is the production. Yeah, and this is typical. Maybe we forgot to mention here. This is typical for TLPs and spars, and I think there are some semi-subs that also use this, but I'm not sure. Okay, one thing that is important to mention is that this causes, you see that this guy, let's see, okay, this guy, if he's floating, then he's going to be moving up and down. It has significant movement up and down. While this one, it shouldn't, the support shouldn't move up and down together with the vessel, okay, because then it means that it's stretching this riser and it's shrinking the riser, okay, or maybe moving it left and right. So this is an undesired situation because you can create a lot of stresses on the riser, and then you might, for example, cause fatigue, and you might cause failure. Also, if you have too much drifting of the structure, okay, let's say, or too much heave, movement in the vertical direction, then this might, for example, here the seals are going to be lost between the tubing hanger and the ball. Okay, so then you might have some leakage. So this is something that is usually undesired. So one way that I do that is that, for example, okay, so we have our well here on the seabed, our subsea, and then we have coming out, and what we do is that we can use, for example, some cans, air cans, okay, that these are holding the riser vertically in place. Yeah, and then we have the structure. For example, if it's a spar, okay, then we have the structure. And then we have here a deck. Okay, let's say here we have a deck, we have a person here. Here we have part of the valve to connect the manifold, and here we have, so this part is going to be fixed always in place, okay, to avoid any causing cyclic or causing deformation on this riser. This is going to be always in the same location. This part, let's use colors now. It's going to be fixed. This is going to be moving. Okay, for example, up and down. Okay. Let's put the sea level. Okay, very important. Okay, remember in this case, for example, the sea level has to be where, of course, the air cans are. Okay, and then you have a flexible, for example, you can have a hose that simply when this moves up and down, then you have some flexibility in this line to transfer the fluids. Okay, this is more or less what I want to show here. So you have the air cans, okay, you have the Christmas tree, and then you have the subsea wellhead. Again, this is how the cans look like. And I'm not sure if I have. Okay, but this indicates that you need to house, so you need your offshore structure needs to house all of these cans, okay, which if you're going to have dry Christmas trees, it affects the size and it affects also the cost of the structure if you need a lot of wells. Okay, another approach that is also used instead of using air cans, and this is also typically used for subsea drilling, okay, for deep water drilling, okay, is where you, instead of having the cans, you have some tensioning system. These are some hydraulic pistons, okay, and you hold the riser with a ring, okay, with a load ring, and then you have a roller. So this part is fixed all the time, and this is moving up and down. Okay, so this is moving up and down, and this is fixed. So with this tensioning system, you're actually controlling that you keep it always in the same location depending on the movement of the vessel. Okay, so you have here one example. This is this load ring. Okay, and then you have these pistons, and they are controlling, simply keeping it all the same place and adjusting the distance depending on the movement of the structure. And this is something a bit critical, because if you're expecting a lot of movement, then you might not be able to have dry Christmas trees. Okay, you have to have a riser, a more flexible structure that will allow to take that big movement. So typically, dry Christmas trees are used when there is limited movement on the vertical direction. So you say only floating structures like Spar, TLPs, and some semi-subs, I don't think there are many, have small movements. They have movement, considerable movement, and let's say this can be up and down 3 meters. Okay, but these are movements that are considerable low for suitable for dry Christmas trees. Okay, it's also possible that if you don't want to, because the drilling package is expensive, so it is possible that you, like in this case, you have a jacket, you were drilling the wells from a jackup. Okay, you see the jackup sticks out the tower, then drills the wells, and then can be used also to do intervention. So in this case, the jacket doesn't have to have a drilling package, which saves on cost. But at the same time, in the future, if I have to do some operation in the well, I have to call this guy to ask for the service.
From them
On the function
or from a
Okay, here you have this animation.
20 meters have 3 or 4 large latticed legs. The rig is towed.
Okay, it's being hoisted up. the platform. And then finally, this one is going on some rails and then is placed exactly on top of the jacket. Okay, another photo. This is also, we have seen it before. I see here is the same thing. You have a jacket. This is in the field of Valhall, where you have a jackup that is performing drilling operations in this jacket. Also, you can have drilling. In this case, this is the semi-sub of Njord, field in the Norwegian continental shelf. And you see you have subsea wells. These are the subsea wells, and these are the risers of each well. Each well has their own riser. But in this case, the semi-sub is located, it has a drilling package and is located exactly over the wells. So if they need to make an intervention on the wells, this is a way simply I go down and I make intervention or a drilling on this location. Okay, so this is a way that I have a floater, and I have subsea wells, but I still can do intervention on the wells. Now, wells are arranged on the seabed in two ways. So one of them is on templates. So wells, in this case, you see this is the Christmas tree, and you have a template that you have 4 slots. Okay, 1, 2, 3, 4. These are the 4 wells, and they are grouped in under the same template. And the intention to do that is because then when you come with a drilling ship on top, let's say you're going to drill these wells, you can just be moored on the same location, and from there you can drill all wells, okay, simply by changing a bit the tower, changing slightly the position. Yeah, but then these wells, they have to be deviated because they have to reach different targets in the reservoir. Another thing is that the wells, as you know, they need some to control, for example, the instrumentation. They need the hydraulic line to open and close the valves. They need a lot of things. They need the chemical injection line. So instead of having one per each well, that when they are located in different places, you have just one cable that it reaches umbilical, that reaches the template, and then from there is distributed. So the template not only has to be a 4, that's used very much in the Norwegian continental shelf, is very popular, but you can also have a template that has many wells. Now the option is to have satellite wells, and in which the wells are not on the manifold, they're not on the template, okay, but they are outside. But then you have to commingle their production into this is called a manifold subsea template. Okay, here you have some lines. You see these are like rigid pipes that they go from the wells to the subsea manifold. Here you have another approach where you have 3 wells, and then you have this subsea manifold. Here, note this thing that I told you about the umbilical. Here you have one umbilical coming from the field. You have a subsea distribution unit that this one is giving what each well needs. Okay, it's giving an umbilical to each well. In this case, you don't have it in the template because you have just one umbilical getting to the template, and then from there it distributes what it needs. You have 2 types of, for satellite wells, if they are closed, you have 2 types of jumpers. One is the horizontal jumper and the vertical jumper. Vertical is more suitable for deep waters because you have it's more easy to install due to gravity, due to weight. But in this case, it's more used to shallower deployments. So how to decide between template wells and satellite wells is a bit of a similar dilemma to dry versus wet. Okay, here wells are drilled from the same location, so they have to be deviated, but there is no need to spend rig mobilization time, and they are cheaper. And also there is less subsea equipment because you don't need the subsea distribution unit in this case. Well, in the satellite wells, they can be shorter, vertical wells, for example, but the drilling rig has to be mobilized between them often. And you need also more jumpers, flow lines, pipeline. You need to have an additional subsea manifold. So it's a trade-off between these two things. In the Norwegian continental shelf, it's more common to have this concept. Okay, so now let's talk about, we talked about the manifold, but actually what it does and how it looks like. We have to make a sketch. Okay, and one of the main functions of the manifold is to commingle the production of the wells. So when we have, let's say we have well 1, we go and produce to the manifold. We typically have, on the manifold, we have a one-way check valve. Then we have a valve. It's called a routing valve. And then we have a header. It's called a header. It's called a routing valve. This is a non-return valve. And then from this header, you have the option to go to, for example, let's say topside. Let's say this can be on a platform or it can be on the seabed. But this is typically on the platform. Okay, but this part here to the left, it can be also on the platform, depending on the type of wells. Okay, if you have dry Christmas trees, then this will be on the platform. If you have subsea wet Christmas trees, then this will be subsea. Okay, so you have the same. Now there is one thing that the manifold, so it's commingling. You have also the, let's say you have another well here. Let's put one more. Okay, so you commingle in this, you commingle production of well 1, 2, and 3 in this header, and then from there is sent further to the facilities. This can be short if, let's make that comment. Short line if dry Christmas trees, or long line if wet. Okay, but another function that it has, so let's write it here. The function is commingle production. Okay, but another function, very important function that it has, is to route production, to be able to route or distribute production. So the way this is done, let's say we have another header, and this header goes to another. Typically on the platform you have production train A, and then you have production train B. Okay, or it could be also test separator. We're going to see in the second part of this lecture, separator should be okay, that I'm using to test the well. So then I have the option, each well to be produced either to the production, or I put another valve, routing valve, or to the test. Okay, the same thing here. Yeah, and on this one I can decide where to send the production of well 1. Okay, I can send it, this one should be open, this one should be closed, and then I send it to production train A. But if I want to send it to the B, then I can close this valve and open this valve, and then the well will flow to production test B. Okay, so this is another function of the production manifold. Okay, so redirect production. And this is important for testing. It can be also to avoid bottlenecking. Okay, for example, if production train A bottlenecks has a lot of gas, and we know that well 1 is a very gassy well, so then we can just close and open this valve, and then we send it to another separator, which is not it can have more capacity, gas capacity. Okay, so then all of this is what we call the production manifold, this structure. All of this structure is what we call the production manifold. It's called production. It can be on the platform or subsea. Okay, now we see how it looks like schematically. So let's see how it looks like in real life. This is of an onshore field. On an onshore field. So see here, these are the lines that come from each well. Yeah, and then they go to two lines. Okay, you see this one is very small, so probably is used for test. Okay, this won't take the full production of the field. And this one is very big, so this one will be the line for production. And here you have the two routing valves. Okay, the routing valve to send the production of well 1 to production or to send it to the test. Okay, you have many wells here. I think this field is in Libya. When you are going subsea, so you have, remember the case that we said, this the template wells. Okay, you have 1, 2, 3, 4, but you have here in the center this manifold, the production manifold. Okay, and the idea is that it's a module that I can retrieve. If I have any problems here, I simply close production from the well, so I can retrieve and replace. To see the manifold, let's see if we see one of the structures that we so these lines here, they are the connection between the well. This comes from the well to the template, to the manifold. Okay, and then it goes and it breaks into two valves. Okay, so these two valves, they are so big because they are controlled hydraulically, so they need to have a lot of the actuator is big. Okay, it's a piston, but essentially this can split the fluid either to send it to this pipe. Okay, so it can either go to this pipe or can go to a similar pipe that is on the other side that you don't see because it's covered by all of these lines. So this line here will be essentially this header, okay, and the other line will be with the one that is behind will be the other header. Okay, so it goes from the well. Either if this valve is open, then we'll go to the other header, or if this valve is open, then it will go to this header. So these are, let's make some comment here. These are routing valves. Okay, we are going to see a bit later what is this thing here. It's this is the crossover valve for pigging. We are going to see later what it is. Okay, and these valves, they are actually they are called hips. These two are called hips. So I think this stands for high pressure protection system. And these are because typically all the system up to this point, up to upstream this point, all of this is made to withstand the full reservoir pressure. So when the well is fully open, you close the rate completely. So all of this is made up to specification that is able to take the full well reservoir pressure. However, the system downstream, which is the system that it will be on the subsea, so it will be like the whole subsea system. The system is typically rated for a lower pressure because then I can make the wall thickness thinner. I can save a lot of material. I don't have to make things that robust and big. Will be if they are big, they are more costly and they are difficult to transport and install. So these hips, the only purpose they have is to, if they see an overpressure, let's see someplace here the flow is getting stopped and then the pressure is increasing, they are responsible for closing a these two valves and then disconnecting effectively this system which is made for high pressure with that system which is made for low pressure. Again, they have a lot of logic, redundancy logics, a lot of protection in place to avoid exposing. If for some reason the flow is close here, then you want at all means, by all means, to avoid that this pressure will reach a very high value. Okay, so let's try to make a sketch of how it looks like. Just to clarify, just to make sure that you understand what. So first we have the well, the places where the wells are. I'm going to exaggerate a bit here. And the manifold is here in the center. You have two lines. So we have the two lines. Okay, if we have two lines connected, then we have the header. Let's put it in another color. Then we have, let's say we have well 1, and then that well we have just one line. This crossing will be this connector that you have here. Okay, and then you have a splitting point where you have either a valve to go to this location or you have another routing valve to go to this header. Okay. So this valve is one of these two, and the other is also one of these two. Also the same thing for this one. You want to have just one point because this connector, you want to be able at some point to disconnect. If you need to do maintenance on this module, you need to be able to disconnect the whole module. So in that case, it's not good that you have many, like if this split is here, then you will have 2 points of transfer, and then it will be more expensive. It's better to have just one. Okay, and then after that you have valve, and then you have and this one also could be done here. Okay, then the last thing I want to comment is on the weight transfer. We are a bit concerned also on the weight on this template. Also when we refer to the offshore structure. So we have our template, subsea template, manifold. Okay, let's say this is a 4-well. These piles that are actually supporting the weight of the manifold, these are typically suction anchors. Okay, if you don't remember what they were, remember we have something like this. We have the soil, here we have some fluid, and then we have a pump that we suck, take out the liquid out, and then this creates a negative pressure, and then this simply will be driven down. Okay, but so these are support the weight of the structure of the template. But if you remember, the wells are actually supported by the soil, okay, are supported by the conductor. So in a way, they are decoupled. Let's put here the four. We should put just this manifold in the center and the two slots. Okay, that's the manifold. And here we might have a well. So let's make that a different color. Okay, we have well. Okay, then here we have the Christmas tree. Okay. And then this is connected with some flow line to the manifold. Okay. This one, the weight of the wellbore is actually goes to the conductor. Okay, it's actually okay. The weight is carried by the conductor. So these two, it means that they are attached with this pipe, but they are actually not supported in the same way. So the well, it could be that due to thermal effects, for example, when you're producing, the well heats up and then it starts to expand. So this is going to go up while the rest of the template is going to stay in the same place. So then this piece of pipe is going to be subject to deformation and stress. Okay, also the same thing, if now, for example, you are stop producing, the well is cooling, is going to shrink. And again, this piece is going to deform. So for that, you see that you have this um, arrangement is simply to create some flexibility to this line such that it allows it to go up and down due to the thermal expansion of the wellbore and don't break. Okay, it gives flexibility to the system to avoid break. That's it.